and welcome to week 2 of ecology this semester. This week we're going to talk a little bit about the types of environments that you can, very broadly, the types of environments that you can find in the natural world, and the abiotic and biotic factors that influence the organisms that live in them. And to talk about aquatic environments today, I've worn one of my favorite dresses that has a little clam on it. There's clams printed. Maybe I can get up and show you the clams printed on the back. On the back of this, there's also clams printed on it. Special occasion dress for talking about aquatic environments. So let's get to it. Okay, here's a fun gift to start off this lecture of a little Dumbo octopus. A picture of my smiling pet sea slug that unfortunately got eaten by a sea anemone. Some funny internet stuff about aquatic environments from a comedian. So let's do it. So first, before we talk about aquatic environments, we have to talk about how they're made, and that's with water. So let's do a little overview of the water cycle. Hopefully this is a review for most everyone. Usually you learn this in like middle school or high school about the water cycle. So we'll start with precipitation. That's the main way that water gets into an environment. That precipitation then either gets intercepted by a tree and then utilized by that tree. And then some of it, though, ends up as surface runoff, which then makes its way into rivers. And some of that infiltrates into the ground, through the soil, and that's called infiltration when it goes into the soil. So any water that comes as precipitation is not intercepted by plants and doesn't soak into the ground, is then considered surface runoff. That infiltration, as it makes its way through the soil and into the bedrock, which we'll talk about in a little bit, then becomes groundwater. And then that groundwater then makes its way into rivers from there. You also have water in the environment via transpiration from trees that are releasing water, and then you also have evaporation from surfaces on the land, but also from bodies of water. And so the combination of transpiration and evaporation is called evapotranspiration. So the evapotranspiration, the definition that you'll want to know for an exam, is the sum of the loss of moisture by evaporation from land and water surfaces and by transpiration from plants. So it's the sum of the loss of moisture. And the two ways that moisture can be lost from the environment is through evaporation from rivers or from the land, or through transpiration from plants. So that's the water cycle. And then you get water in the atmosphere again, and then that comes back down as precipitation. Water has some physical properties that are going to be really important for determining the ecology of the organisms that live in aquatic environments. They have really high specific heat, which means it takes a lot of energy to heat it up. That's really important. There's also a density-temperature relationship, which is basically ice when it's frozen. Water when it's frozen is less dense than liquid water, and so because of that, it will rise to the surface. We also have surface tension due to cohesion, and that's going to create strong bonding forces on the surface of water. And then high frictional resistance due to viscosity, and then buoyancy due to high viscosity. And in class, in our in-person sessions, we'll talk about why these important physical properties of water dictate the organisms that live in aquatic environments. Light also varies with depth in aquatic environments. Here's some graphs from your textbook. So this is light percent surface at the surface of a body of water. You've got 100%, but as you go deeper and deeper, you've got much less percent light penetration at the bottom. This is at 100 meters. You also have different wavelengths penetrating different depths within the ocean or any body of water. Usually the ocean's the only thing that's going to get this deep. And so again, light availability is really important for organisms to grow, and so that's also going to affect the organisms that live in aquatic environments. So this is a really good graph here and here of the different types of wavelengths that can penetrate the deeper depths. So you're only really going to be getting shorter wavelength penetration into deeper parts of the ocean and deeper bodies of water. And because of that difference in light penetration with depth, you're also going to have differences in temperature, because with light brings with it a heat that warms up bodies of water. So here's just some illustrations of what's called a thermocline. A thermocline is a layer in a thermally stratified body of water in which temperature changes rapidly relative to the remainder of the body. And so it's this area in here between stable regions of temperature and bodies of water that's called the thermocline, and that's where temperature changes rapidly. So you also see that here too, this zone of rapid temperature change. And then the epilimnion is the surface above. You've got more light penetration, more wavelengths coming through here at the surface, and because of that, you also have warmer water at the top of the surface. It's also a lower density. And then you have the hypolimnion, which is cold, higher density, deep waters. And how constant this stratification is going to depend on how deep the body of water is and the flow of the body of water. And we'll talk a little bit about that in person as well. So if you have a deeper body of water, you might have a more constant thermocline. If you have a shallower body of water that has a lot of agitation, this thermocline is not going to be as stable, but it just depends on the kind of environment. In some organisms in really deep bodies of water, like the ocean, this thermocline is definitely going to be more stable because that depth is less disturbed by surface disturbance or disturbance below the surface. And we're going to talk about in person this really cool adaptation to the deep sea and anglerfish and the little dude that's hanging out right there. Another important thing to consider when we're talking about aquatic environments is that a lot of things will dissolve in water, and that's going to influence the organisms that can then live in that water. This is a graph looking at the mineral makeup of the salt in seawater. So here is just a diagram of the amount of salt that's in 35% salinity seawater. But these are all the different minor and major mineral constituents that make it up. So it's not just sodium and chloride, it's a lot of other things too. And those are going to influence the organisms that live in it. Now, the ocean water is going to have a lot more solutes in it than freshwater will have. And freshwater is constantly flowing into ocean water. And then the main way that water is lost from the ocean is through evaporation. And so the ocean over time has gradually become more and more salty. Some of that will precipitate out, such as calcium, and will deposit in places. But over the last few million years, the ocean has gradually been becoming more saline. So the things that are dissolved in water are going to be really important for ecology as well. Oxygen is one of those things that can diffuse into the water, and it will diffuse from the atmosphere in through surface waters. And the pattern at which oxygen diffuses into surface waters is going to change depending on the type of body of water. We're going to talk a little bit more about that in lecture in person, about the ways that oxygen makes its way into water. But here let's talk a little bit about how that oxygen diffusion can change temporally depending on the temperature that it is outside. So in the winter, this is just a small body of water, like a lake, a small lake or a pond. In winter, you're going to have a layer of frozen ice on the top. And so you're going to have high O2 concentration in the middle and then lower O2 concentration at the bottom and then medium near where the ice is. But you're not going to have a lot of oxygen diffusion happening there if ice forms on the top. And that's what you see here in this graph of the winter here, is that this colder water, while it does increase the oxygen solubility, if that water is so cold that it forms ice, that can also reduce the diffusion. So if it's colder, it'll increase the solubility of oxygen, but only to a point until it freezes. Then when that ice starts to thaw in the spring, and you get a circulation of the temperatures, so the cold water will sink and the warm water will rise, and that will cause a circulation of temperatures in the spring. And so you'll get a more even distribution, but still some bit of a thermocline in the spring. And that's also going to help with nutrient cycling, which we're going to talk about later on in the semester. And then in the autumn, you have the same thing with changes in temperature. So in the fall, as you see on this graph, so this is for this is the vertical profile of oxygen stratification in a lake in New Hampshire. In the fall, this lake is the most stable in terms of oxygen and temperature, because that oxygen is being constantly surfaced from the top through the water, and so it makes it more stable. And then in the summer, things are more still in the water. You don't have as much oxygen cycling, and so that's when you have a pretty definitive thermocline, where you have this rapid change in temperature and in oxygen levels. And so because of these cycles, these seasonal cycles that you have in bodies of water, depending on temperature, and then also on oxygen availability that are going to fluctuate with the seasons, you also have organisms that have evolved these really interesting adaptations to survive with really low oxygen and low temperature. A couple of examples are lungfish and arapaima. These are fish that are adapted to live in low oxygen environments. And then also mosquito larvae are a cool adaptation because they have these little tubes that come out of the butts of the larvae that go up to the surface, and that allows them to acquire oxygen when normally the larva is developing in a body of water that has low flow and low oxygen. So this is the reason you find mosquito larvae inside of old tires or old buckets of water that are sitting outside, is that they like low flow environments, but they have these special adaptations to obtain oxygen from low flow environments. Acidity is also going to have an influence on aquatic environments and the type of organisms that can live there. At neutrality, most of the carbon dioxide that's going to be present in water is going to be present as bicarbonate ions. At a high pH, more of the carbon dioxide is present as carbonate ions. And then at a low pH, that's when you have more carbon dioxide that occurs just in the free carbon dioxide condition. And so this is going to affect how organisms utilize this in the environment. Now, around here in Pennsylvania, we have a lot of limestone rock. And when that limestone, which we'll talk about in the terrestrial lecture, when that limestone weathers, the limestone calcium carbonate then makes its way into the bodies of water. It dissolves in there as a solute, and that's going to make it a higher pH when you have the contribution of limestone. And even in some streams, when they're too acidic, you can actually add crushed limestone to them to help buffer the system. Now, having low pH can be really, really bad for a system. If a pH is below 4.5, then heavy toxic metals like aluminum become soluble in the water, and those are extremely toxic to aquatic organisms. And so having a low pH is really, really bad for lots of aquatic life. And water movements are in their shape. Water movements shape freshwater and marine environments. So we're going to talk a little bit in person about the effect that velocity has on the amount of oxygen in the environment, and then the special adaptations that animals might need to survive in an environment with high flow and high velocity like this versus a more standing pool that maybe has a little even more nutrient deposition from the shore coming into it, and we'll talk about that in person in class, how, the effect that velocity has on organisms in the environment. Now, special areas that will have their own lecture later on when we talk about ecosystems are marine coastal environments. Tides are going to affect a lot of the different types of organisms that live in marine coastal environments. So this is a beach. This is Dana Point, near where my family lives in California, and this is us visiting the beach at high tide. So this is the water up at its highest level. So you see this tiny stairwell right there goes all the way down about 20 feet lower during low tide. And during low tide, lots of rocks and surface area are exposed, and there are organisms that are especially adapted to live in these kind of highly fluctuating environments. Just a few examples are things like barnacles. Barnacles can close up. They are actually a type of crustacean, but they can close up inside of their calcareous shell to protect them during low tide when they're exposed. So they need the water, and they can dry out if they're exposed. And so they close up in here to protect themselves during low tide. This is a chitin. This is another invertebrate. It has this hard shell, so it attaches onto rock surfaces, and during low tide it presses itself down so that its soft fleshy body that's underneath this shell doesn't get exposed and desiccate. And then this is just a cute snail. Obviously this gastropod can go inside of its shell when it's exposed to the air and not fully submerged, so that it can protect itself from desiccation. So a lot of animals and plants that live in marine coastal tidal environments have special adaptations to dealing with constant fluctuations in salinity and temperature and in water availability. Here's some other ones. This is a Christmas tree worm that can go inside of its tube when it's exposed to the water. Here's another chitin. Here's another Christmas tree worm. Here is a sea anemone. There's lots of individual animals that you can see of this picture if you look a little close. There's another chitin. There's one here. There's a little bit. Oh, this is actually another sea anemone. So this is a sea anemone that's open, but when they get exposed to the air, they can completely revert in and avoid desiccation. And this also protects them from changes in salinity as well. So when they have more water, that's less salt. But when the water recedes, some of that salt then collects as a residue, and that salt can be dangerous. And so these shells or these tubes that they live in, or being able to close in on themselves, can protect them from salt damage too. So those are marine tidal environments. You can also have these areas called estuaries that are the transition zones between fresh and saltwater environments. And these present their own kind of unique constraints as well. So in an estuary, there's a vertical and a horizontal stratification of salinity from the river mouth to the estuary at high tide, which are the brown lines here, and then low tide, which are the blue lines. So when high tide comes in, you've got incoming seawater is going to increase the salinity in these estuary environments. At low tide, the salinity is going to be reduced because you've got more fresh water than salt water. But then also when we think about depth, salinity is going to increase with depth because fresh water has less solutes in it, so it's less dense than salt water. So you've got more salt down here, more fresh up here, and then depending on the tides of the day, at low tide versus high tide, you're going to have more or less fresh or salt water in these estuary environments. So constantly fluctuating differences in salinity are going to be challenging for organisms to adapt to too. And just two examples of organisms that have learned to deal or have developed adaptations through evolutionary time to deal with these is one is the salmon. So salmon are born in freshwater. They then swim out to the ocean, and they spend most of their life in the ocean, and then they return to freshwater to spawn. And then they die in those freshwater environments. So when they're in the ocean, the salmon will drink several liters of water a day in the ocean to deal with these changes in salinity, so they're bringing in more water. But when they're in fresh water, because there's almost no salt there, they drink hardly anything at all. You would think, obviously, a fish drinks in water, but how much water it's actually passing through its gills changes dramatically depending on if it's in salt or fresh. In fresh water, they're going to produce lots and lots of dilute urine. There's plenty of water without lots of salt in it, and so they'll constantly be processing and passing dilute urine. But when they're in their saltwater oceanic environments, they make super concentrated urine to excrete a lot of those salts, but retain the water without the salts in the ocean environments. When they make that transition, so say after they're born and they're making the move out to the ocean, or when they're coming back to spawn, they'll actually spend several days or weeks in the brackish water, which is a lower salinity than the ocean, but a higher salinity than the freshwater. They'll spend a few days in there acclimating to the change in saltwater before they make the full transition. Because can't imagine the physiological damage that would do going from a hugely saline environment to complete freshwater. Another organism are red mangroves. These are some red mangroves here that you can see their prop roots that are holding them up. Some adaptations that they have to deal with these saline environments is that the leaves of these trees have glands that secrete the salt that they're constantly bringing in from this brackish water. So brackish is just basically not as salty as seawater, but not freshwater. So they live in these brackish environments and they excrete their salt through their leaves, but the leaves are also waxy to prevent water loss. So they need to be able to retain water while losing salt. So they have special glands for excreting salt. And then these prop roots that they have, which you learned about in Gen Bio, these help support it in sandy, unstable soil. So if this sand provided more structural support, then they could be, built like a terrestrial tree. But the sand is really loose and is constantly being sifted around and moved, and so they need these prop roots to support them in really unstable, poor soils. And to end this lecture, I'm going to play a video that my dad took of a flock of pelicans at that place I just showed you a video from. Oh, actually, this is in San Clemente in California. My dad just sent me this video today of a intertidal species that's really important, and we'll talk about shorebirds and other things at the end of the semester when we talk about coastal ecosystems. So that's it for aquatic ecosystems, at least for now. We'll come back to them later because in ecology, everything is hierarchical. So we will see our watery friends soon. Bye-bye!